What's up, guys? Another video on structure and bonding. This time we're looking at my least favourite topic, shapes of simple molecules. And I don't like it particularly because there's a lot to revise, it's pretty niche, and also you learn at university that it's not particularly precise either, it's not particularly accurate. But we've got to do it, let's do it. Before we start though, please like, subscribe, share. I want to grow those viewer numbers so that this can help as many people as possible. Let's get to it. So the easiest way to start is to really look at the sort of visualization of what these things look like. So if we take methane, for example, methane we know is CH4. We know we've got 4 hydrogens attached to that central carbon. And the way we'd sort of draw it, something like this. Carbon, your hydrogens, and add your dots and crosses. Now, this is a simplification, right? A methane molecule doesn't sit like this in space. This is how it sits in space, okay? This is our methane. Now, what we can see is that these pairs of electrons that are our covalent bonds repel each other, okay? And so we get these fixed shapes, okay? We get these fixed shapes. This is what we call a tetrahedral shape. And we've got an exact bond angle between these. These are all 195 degrees centigrade between, not degrees centigrade, degrees between each of these bonds. These are fixed bond angles that we need to remember. Okay, so if we come back, again, that's different to what we've got here. Now, the way we draw this very often is like so. So we've got one carbon. We try and show that these are in 3-dimensional space. So what this shows is that the covalent bond is coming away from me. These show that they're sort of flat, and this triangle shows that the hydrogen's coming towards me. So it's our way of sort of trying to show this, right? Showing 3-dimensional structure but in 2-dimensional space. Now, let's go for another example. Let's do water. H2O. We know looks something like this, right? So we've got O, H, H. But it's a bit more complicated than that, right? So again, if we draw our little dot and cross diagrams, oxygen's in group 6, so it has 6 electrons. We'll replace those lines. So we need 4 more electrons. So we haven't just got these 2 bonded pairs, we also have 2 lone pairs. And again, that will affect our structure. This is what we get. Now, if you can see, now we've got these lone pairs in there as well. So these lone pairs actually repel more than the bonded pairs. So they squeeze these bonded pairs together. I've sort of drawn a little diagram of that here. So again, we've got lone pairs of electrons. And we've got bonded pairs. What we need to know is that electron pairs will repel as far as possible. But that lone pairs repel more than bonded pairs. And this will become important when we start to explain why we get particular bond angles. And these are the ones that we need to know, okay? So we've got two bonded pairs. We've just got linear. They've repelled so far as possible. We've got three bonded pairs, trigonal planar. Here we've got bent, and that's what we've just looked at with water, where we've got two lone pairs and two bonded pairs. Pyramidal, we've got three bonded pairs and one lone pair. We've got this angle of 107 degrees. We only need to know the angle between bonded pairs. We don't need to know the angle between bonded and lone pairs. Going across, we've got tetrahedral, which is the shape of methane. We've got an angle of 109.5 degrees, as we looked at before. Square planar, here we've got 4 bonded pairs and 2 lone pairs. Trigonal pyramidal, where we've got 5 bonded pairs. You might be thinking how that can happen. We'll look at an example later on. And we've also got octahedral, 90 degrees. Yeah, trigonal pyramidal is a mad one in that we've got two different bond angles. So there are 90 degrees between them. Then we've also got this, which is 120 degrees. Let's just look at what that looks like. Not that one. Not that one. Yeah, it looks like this, right? So you can almost imagine, if I angle this right, you've almost got this flat triangle with two sticks coming between them. So everything here is 90 degrees, but this sort of triangle and this horizontal plane, there's a 120 degree angle between all of those. And then octahedral, a bit easier to visualize. Anyway, these, again, unfortunately, you just need to remember. You need to remember if we have two bonded pairs and no lone pairs, we're linear. What I'll do is I'll put a link to some notes from Physics and Maths Tutor that has all of this in more detail. These are the most common ones though. Let's look at some examples. So we'll start off with ammonia. And I think it's helpful to start off with quickly drawing what ammonia looks like. So nitrogen is in group 5, so we've got 5 outer electrons. So it's going to form 3 covalent bonds, then we've got a hydrogen as well. So I think it helps to start to quickly draw out a dot and cross diagram. So we've got, start off with your central atom, which is nitrogen in this case. You've got your hydrogens. We've got our bonded pairs. So here we've got 3 bonded pairs. But remember, it's in group 5, so we need 1, 2, 3. We need 2 more electrons. So we've got 3 bonded pairs and 1 lone pair. Let's have a look at which one that is. Okay, that's here, pyramidal. So let's draw that. So we've got N. We draw our dashes coming away, hydrogen. Our dashes coming to triangle coming towards us, hydrogen, hydrogen, and it's important as well that we draw our lone pair, something like that, as well as our bond angle. So we've got a bond angle of 107, and we call this pyramidal. And here, when it comes to our explanation of this shape, we say we've got 3 bonded pairs and 1 lone pair. And then you have this explanation afterwards. Electron pairs repel as far as possible. Lone pairs repel more than bonded pairs. And again, that's like we've had before, our sort of catch-all. That's going to be a really useful turn of phrase for us. Then we come on to ammonia. So, ammonium, sorry. So we've got this. Now, this is a good opportunity as well to talk about dative covalent bonding, or coordinate bonding, right? Because what we've got here is we've got this lone pair of electrons. So if there's something that needs a pair of electrons in order to get a full outer shell, they can attack this. So what we get is we can get an H plus ion, which of course has no electrons in it at all. That's why it's got this positive charge, can now come and attach itself to this. So what we get is this. So this now constitutes 4 bonded pairs. And of course, got a positive charge. Notice I've got 2 crosses here. We haven't got the dot and cross showing that we've got 1 electron from each. So 4 bonded pairs, right, we've got tetrahedral. So let's draw that. We've got our N, and we draw an arrow like so. And this arrow shows that both of our electrons here have come from the nitrogen, hydrogen, this is our tetrahedral shape. And we've got a bond angle of 109.5. And again, this time we say we've got 4 bonded pairs. And then we've got the same line as before. Electron pairs repel as far as possible. Lone pairs repel more than bonded pairs. Okay, now we've got a couple more examples here. So one thing we do need to know is that anything in period 3, particularly the stuff over here, can act a bit funny. Because we've seen before that we've got, it basically has access to this 3D orbital, right? So what that means is sometimes it can change that rule where we need a full outer shell. So sometimes phosphorus and sulfur in particular can have more electrons than, say, phosphorus would need 1, 2, 3 to have a full outer shell. It can have more than those 3 electrons. So we get something that looks like this, and it looks quite funny. But we start off with our phosphorus. And you can probably guess what this is going to look like, right? We're going to have our CLs dotted around. We know Cl always has a need for 1 electron. And then obviously fill in the rest of chlorine's outer electrons. Something like this, right? So this time we've got 1, 2, 3, 4, 5 bonded pairs. So my advice is, when you have something from period 3, really focus on the thing that it's bonded to. That's the thing that's going to follow the rules, right? The phosphorus and sulfur, not necessarily. So we know we've got 5 bonded pairs. Okay, that's this shape here, right? So we've got phosphorus, something like that. 90 degrees between these, 120 between these, trigonal pyramidal, bipyramidal, sorry. In your explanation here, let me get rid of this. And your explanation here is going to be, we've got 5 bonded pairs. And then we're going to do this bit. Electron pairs repel as far as possible. We don't need to talk about lone pairs, obviously. Last one, SF6, sulfur in group 6. Again, now it can act a bit funny because sulfur's in period 3. We can probably guess what this is going to look like. 1, 2, 3, 4, 5, 6. I'm not going to add the fluorine or the rest of fluorine's electrons because we don't need that for this bit, but clearly we've got 1, 2, 3, 4, 5, 6 bonded pairs, so it's going to be octahedral. That's going to look like this. So S goes straight up, straight down. F. Perfect. Octahedral. Six bonded pairs. And then we've got the spiel here, haven't we? Electron pairs repel as far as possible. That's our explanation. So, the question I would like you to give a go, again, let me rub this out, is this one. Screenshot it, give it a go. I'll answer it at the end of next video. But now let's get on to last video's questions. So here, we were trying to work out which of these has the stronger ionic bonds. Sodium sulfide, let's have a look. Potassium is bigger than sodium, and so sodium is going to have a greater charge density. So let's circle our sodium sulfide. So we've got Na plus versus K plus, that's our difference. Same charge, but Na plus smaller. Therefore, and it's all of this bit, greater attraction between oppositely charged ions, therefore more energy required to overcome the forces. Next, lithium oxide and magnesium oxide. Let's move over. Okay, lithium is going to be smaller, but only a 1 plus charge. Magnesium is going to be bigger, but it's not going to be twice as big. So that +2 is going to have a bigger effect. So, magnesium oxide, and we can say Mg2 plus versus Li1 plus, greater charge, so stronger attraction. Dot dot dot, despite, and I think it's always worth mentioning, despite being a larger ion. Perfect. Next, silver reacts with fluorine to form silver fluorides. Silver fluoride, high melting point, similar structure to that of sodium chloride. State the type of bonding involved in silver fluoride. So we know we've got ionic. Draw a diagram, show how the particles are arranged in a silver fluoride lattice. Show the charges on the particles. So, AgF, we're given the formula. We know F is going to be 1 minus, so Ag must be 1 plus. So we've got a very simple diagram here. Doesn't need to be complicated. Even that will suffice. Show how we're bonded. And now we just need to show, again we've got Ag plus, F minus, Ag plus, F minus, Ag plus, F minus. We just need to show that they're alternating, right? We need to show they're alternating, we need to have our charges, etc. show the charges. But explain why the melting point of silver fluoride is higher than silver chloride. So there, we know the Ag is not the factor, it's the fluoride and the chloride. So there, all are going to be minus charge. Fluoride is going to be smaller than chloride. So F and Cl both 1 minus. F, smaller ion. So, and now we can just use our catch-all here. Therefore, attraction between oppositely charged ions, greater attraction between oppositely charged ions, therefore more energy required to overcome the forces. Hope that's helpful. Give the question on shapes a go. I'll answer it at the end of next video. Until then, happy revising, guys.